Hello, today we're going over Worksheet C just to make sure that we got everything out of it we were supposed to. And let's take a look then at our first set of questions. So looking at the light above, the color that corresponds to the longest wavelengths, well, let's check this out. Here's the wavelengths, and the largest values are up here, and so that would be the red color, and so that's 1A. For 1B, which color represents the shortest wavelengths? So again, looking down to the numbers where they're the smallest, and that corresponds to the violet colors. So then answering question C, looking at the numbers in the table, circle the word that best completes the sentence. The shorter the wavelength, so here's the shorter wavelengths, the blank the energy. So here's the energy column. Shorter the wavelength, well, here's these values compared to the longer wavelength values, so it appears that the energy values are larger down here for the shorter wavelength, and the energy values are smaller up here for the longer wavelengths. So we should have greater circled for that one. Moving on to the second page, I'm looking at this depiction here. You viewed line spectra in the classroom for several different elements. This is just showing for hydrogen and boron. We did look at hydrogen, we did not look at boron in the classroom. But anyway, here's what they would look like. Which color of light corresponds to the shortest wavelength for hydrogen? So again, looking at the numbers, these are the wavelengths. So the shortest or the smallest number we have is 410, and so that's violet. And which color of light corresponds to the longest wavelength for hydrogen? So here is the largest number, and that's red. For 3, looking at the answers we just came up with and what we talked about in 1C, the fact that the shorter wavelengths have higher energy. That's the question we're looking at for number 3. Which color of light has the most energy for hydrogen? So we said before in 1C that the shortest wavelength has the highest energy, so violet would be the highest energy wavelength for the hydrogen spectrum, and then 653, the longest wavelength, would have the least energy because we had said that's the relationship, longer wavelength, the lesser the amount of energy. Question 4 has us comparing boron. So the thing to note with line spectra is that they're different for each element. So hydrogen and boron, we can see that we have different lines in different places, and says, does it emit the same wavelengths? And so no, it doesn't. Even though we've got some similar colors, like there are violet wavelengths on boron, and there's a violet listed in hydrogen, but it's not exactly the same wavelength. So, and we have some same colors, but with different wavelengths. Again, here's a red at 625, here's a red at 656. So even though you might see the same colors in their spectra, you do not have the same exact wavelength. And so that's why we can use these spectral lines as fingerprints, basically, for the elements, because they're different for each element, they're unique for each element. And even if we have some similar colors, we're going to have different wavelengths for those colors. All right, moving on to the next page here. So for number 6, electrons and protons. So we know that electrons are negative, protons are positive, so they should attract each other. So that's pretty important. Number 7, as an electron gets closer to the nucleus where the protons are, the attraction to the nucleus gets stronger. So if you think about it, if you ever put two magnets together, the closer you put the magnets together, the more they want to grab onto each other. And if you separate them a little bit, you can still feel the pull, separate them a little bit more, and so forth and so on. So the closer the electron gets to the nucleus, so the closer these charged particles that are attracted to each other get, the stronger that attraction gets. So that's another very important thing to make note of. Number 8, for an electron to move from an energy level close to the nucleus to an energy level far from the nucleus, it would need to, okay, so if my electrons, so let's just look at this depiction here. If my electron is right here, let's say in energy level 1, and it's being attracted to the nucleus, then in order for me to pull it away, so again, think of two magnets sticking together. If I want to pull them apart, I have to apply energy, right? So I have to pull on them. And so that means that in the same kind of relationship, the electrons being attracted to the protons in the nucleus, if I'm going to pull the electrons away, so if I'm going to move it, say, from the first energy level to the second one, that would be pulling it away from the nucleus, it's going to require an input of energy. So for number 8, we should have a gain of energy. So to add energy in order to pull the electrons away from the nucleus. And for number 9, for an electron to move from an energy level far from the nucleus to an energy level close to the nucleus, it would need to, so in this case it's the opposite of what we just described. So we're losing energy, and if I put those two magnets close enough to each other, they will eventually just naturally kind of go towards each other, and so that's kind of a similar thing where we're, our electron's going to be like at a lower potential energy if it's moving closer to the nucleus. All right, number 10 is energy absorbed or released for the electron transition shown in the diagram above. So notice the arrow is going from the second ring, the second energy level, up to the 5th energy level. So going closer to the nucleus to farther away from the nucleus. So based on what we just answered in question 8, to move farther away from the nucleus, we're going to have to see the electron gain energy. So the electron will be absorbing energy to make that transition, based on what we just said. All right, number 11, looking at the transitions. So you'll notice that there's also different colors shown for these waves that are coming out, showing the energy being released. This is labeled the energy level changes for 4 atoms, so we're looking at which energy level is the electron coming from and going to. So for A, it's coming from 6 and going down to 2, so this should be 6 to 2. And the electron moves from A, so in higher energy level has the higher number, so it's going from a higher energy state to a lower energy state. And is the light absorbed or released? Well, then that would mean that the energy is being released. Okay, so that's why we see this arrow, this squiggle line arrow, so that's the representing the wave of light that's being released. For B, we are going from n equals 5 to n equals 2. So this should be 5 to 2, and electron is moving from a higher to lower energy state, and therefore there's a release of energy. In this one, we are going from 4 to 2, so from 4 to 2, n equals 4 to n equals 2, again a release of energy. And notice that, again, these wavelengths that we have depicted are getting longer and longer the shorter the jump is, so that's something interesting to note. And notice what we talked about before, like the violet color we said has a shorter wavelength and higher energy. So we see this is the biggest energy jump with the violet squiggle, and then we've got the blue, which is a slightly lower amount of energy, and then we've got the aqua color, which is even lesser energy and a longer wavelength, and then this last jump going from n equals 3 to n equals 2, that's a red color, and that has an even longer wavelength and the lowest energy jump. So we see that correlation to what we talked about. So which of the electron transition involves the most energy? Well, I just said that. That would be A, we're taking the biggest jump from energy level 6 to 2. We also see that shortest wavelength and the violet color depicted. And explain why this transition involves the most energy based on your understanding of attractive forces. So again, the closer I'm getting to my nucleus, the more now this electron is starting to feel the attraction to the nucleus, and therefore it's a bigger energy jump. All right, and then lastly, we're supposed to answer this question on our own, so we'll go over this in class when we get in, but again, we said we can use these line spectra as fingerprints, so comparing, this is the line pattern for lithium, and although we don't know what colors these are, and although we don't know what the wavelengths are with what's labeled here, we can compare the line patterns of the different elements. So we notice that lithium, hydrogen, helium, sodium, they're all different, and then we're trying to figure out what's the unknown. So compare these patterns and see if you can figure out which elements are definitely not in the unknown. So if we don't see lines from a certain element in the same place, they must not be a part of the unknown. And if we do see lines from the element, then they probably are contained in the unknown. And again, we'll go over this in class when we get in together.